Welcome back to School of Physics. Another lecture. Today, as you can see the heading, I am going to discuss few problems on the laws of motion which we were discussing earlier. We have discussed the law of inertia, that is first law of motion, second law of motion, and third law of motion. With that, we also discussed the impulse and other stuff which was concerned and dealt with these concepts. And we also discussed the coordinate systems, which include orthogonal coordinate system and plane polar coordinate system, that is polar coordinate systems. We discussed all these kind of stuff in the earlier lectures. So today we are going to deal with few problems or onto these very concepts. Let us take the first problem. Problem number 1. Consider, it is actually dealt with the second law of motion, third law of motion, and furthermore in other problem sets we will discuss other ideas as well. So here, first problem, consider two objects, consider two bodies on a surface. This is surface, but this is frictionless surface. Keep that in mind, it is frictionless surface. This is the first problem. We are considering a frictionless surface, and on that we are having two bodies. This is body 1 with mass m1, and second body is attached with it. It is smaller body of mass m2. The surface is frictionless. Two bodies are side by side placed onto this very surface. And suppose that we are applying in this direction, we are applying a force on body bigger body, that's on body m1. So we have to calculate, this is the horizontal force, keep that in mind, acting over on this very body. What is the problem here? We have to find the force of contact between m1 and m2. This is the problem to be solved. So we have to find the force which is acting between the bodies m1 and m2, not this very force. This very force is acting on the first body only. So since if we apply the force on this very body, that will result in the motion of the second body as well, from the second law of motion and the third law of motion. How that is applied, I will tell you that very thing in a moment. So we have to calculate that very force which is exerted by body m1 onto this very body m2. So that will be the force of contact. So actually we have to find the force of contact. Let us say we denote this very force of contact by F prime. Okay, so how to deal with this very problem, the solution part of this very thing. First and foremost, draw the free diagrams. Okay, draw the free diagrams. Draw the free diagrams. For example, the mass m1, this very body is here. Since the surface is frictionless, so it will not exert any frictional force onto these very bodies, even though these are set in motion on this surface, but it will not exert any force to retard its motion because the friction is absent here. We are considering the frictionless surface. So only the forces which are acting on body m1, this is the body m1, will be first and foremost this very force acting horizontally like this. So this is the force acting on this F. Another force, since it has mass m1, so there will be a downward force exerted by gravitational force, which is the gravity of the earth. Okay, so gravity is always downwards, so we have to keep in mind this must possess some weight, and that weight will be given the downward force equal to mg, that's m1g, the mass of the body, m1 multiplied by the gravity. But we see that this body is not set in motion in this direction. Say this is the direction y-axis, this is the y-axis, and this is the x-axis. Since no motion is in this direction, no motion is there. Okay, no motion, only the motion is seen in this direction, that is the horizontal direction, x-axis only. So that means this mg, that is the weight, must be balanced by some force which is exerted by the surface when these come in contact, which is exerted in the opposite direction, to that of this weight. Since the weight is downward, so there must be a balancing force, which is the reactive force upwards, which must be equal to that of the weight of this very body, and we represented that reactive, the normal force, as R1. So this R1 must be balancing m1g, because there is no motion seen along y-axis like this. So no motion is seen along this very axis, so these must be equal to each other. Okay, now another thing, we have another body here, m2. This is m2. Similarly here, downward force is gravity, so there must be m2g, which is the weight of the body. And this weight of the body, since there is no motion along the y-axis, so it must be balanced by the upward force, which will be normal force to this, and which will be the opposite to that of the weight, a kind of reactive force, denoted by, we'll denote it by R2. So these two must be cancelling out each other. Now there is another force. Since these two bodies, m1 and m2, these two bodies are in contact with each other, so there must be some normal force acting between these two also. And if this is the point of contact between these two bodies, say, so if body m1 is exerting some force on this very body, some normal force on body m2 as n, similar force must be, say for example these two are at rest, okay, even though these are at rest, and then also force of contact will be there, this normal force will be there, because when our two bodies are set in contact, there is some contact force. If this very exerts more force onto this, then this will be set in motion like this. If this exerts more force on this direction, then it will be set in motion like this. So that means there will be always this contact force, and from the third law of motion, there will be equal and opposite normal reaction, normal force acting on m1 also. So this n and this n cancels, so this very contribute nothing to the motion, overall motion of these two bodies. R1 cancels m1g, R2 cancels m2g, so these contribute nothing to the net acceleration or net motion of these two bodies. So we will find that the only force which is contributing towards the acceleration of these two bodies will be this F. Okay, because this F is not cancelled out. All other forces are cancelled out. So F is the only force. So this F is the only force contributing. This F contributes to the combined acceleration of the two bodies, M1 and M2. Okay, so that means this force applied, which is applied now, we have two bodies like this, M1 and this is M2. Force is applied on this F. So only force which is contributing to the acceleration, because if this force acts on m2, that will result in the motion of m2, on m1, that will result in the motion of m2 also, because these are in contact, and contact forces, all other forces are cancelled out. As you have seen, this very cancels this cancels this, n cancels this very n. Okay, so the net force, the net acceleration is caused by this very force, and these two bodies act as a single system with mass m1 plus m2. Okay, so this very body acts as if as it is a single body now with mass m1 plus m2. So we know from the second law of motion says that force equal to mass times the acceleration. Okay, mass times the acceleration. Since we are dealing with the in the horizontal direction only, the force is acting on this direction only, so we will take these as scalars, as this is only the one-dimensional problem, not the vector one. Okay, even though this is a vector, but it's only the single directional. So that means F will be equal to mass of the system. Now we have two bodies at a time taken. Okay, at a time. So we have m1 plus m2, the total mass, that is m1 plus m2 times the acceleration. So this is the acceleration which we are unknown till yet, because force is known, which is given in the problem as F. The mass of the two bodies is given, so we can calculate the acceleration. So till now we have got force acting on the system as mass times acceleration, that's m1 plus m2 times the acceleration, which further implies that the acceleration will be equal to the force upon mass of the two bodies, that is mass of the system. So this will be the acceleration caused inside the two bodies. Okay, so the two bodies, that is these two bodies, will be accelerated with an acceleration of a given by this very formula here. Okay, so this will give the acceleration of the two bodies of m1 plus m2 as a system, but we have to find the contact force here, the contact force between these two. So that very force will be given, since force is acting only on this very body F here, isn't it? So this very F causes motion in M1, so that in turn causes motion in M2. So actually the force of contact is affecting this very body M2, this very body M2. So we have to find the force which is acting on the M2, that is the contact force, because this very force acts only on M1, and the second body is an in turn, due to the effect of the bigger mass which is in contact with that very causes the motion in M2. So we have to find the motion, we have to find the force acting on that very M2 body. Suppose the force acting on the M2 body, that is the force of contact, we have represented that F prime will be given by second law of motion, that is m times acceleration, and m here is m2 times the acceleration. Since acceleration, this very acceleration is same for both of the bodies, because both of the two bodies are combined or moved in combination due to the force F. Okay, so this very body M2 will be moving with the same acceleration as that of the two bodies, because these two bodies are set in motion in a combined state. Okay, so this very acceleration will be same for this very body or as of that of the whole of the two bodies as a system. So the acceleration of the system, here I will write it system, acceleration of the system is given as this. Since acceleration of the system is same as that of the acceleration of M2, which is equal to the acceleration of M1. Okay, because all the accelerations are same. This M1 is moving with the same acceleration as that of the M2, and M2 is moving with the same acceleration as that of the combined system. So this acceleration is actually this. So we will get F prime equal to mass times, that is the mass of the second body, multiplied by acceleration of the system here. I will write it down, it will be same as that of the system. It is F by m1 plus m2. So this will be the force which is exerted on body m2. So this will be the force on m2, and that is the force of contact. Force of contact between m1 and m2. So we have calculated the force of contact from second law of motion between these two bodies which are given in the problem set. Hope you got that. We'll try to solve another one in the next. Now we will discuss another problem which will be dealing with the similar effects, which are the first law, second law, and third law of motion, and also will be dealing with the normal forces, contact forces as well. So we have another problem. The problem second. Here we have we have a particle inside a vertical cone. Here also frictional force is absent. So we have a cone like this. Okay, we have a cone like this, and the particle is moving inside it. This is the particle moving inside this cone in a circle. Since if it is set in motion inside this cone, it will be moving with the circular motion like this. This will be a circular motion. This will be a circular path followed by this particle inside this cone, having some radius of this circle, not the cone, radius of this circle, which is exhibited by this particle. Okay, so this will be, say, the radius of this path is r. And another thing you have to keep in mind, the half angle of the cone, that is slant height here, it's slant angle here. This angle is theta, half angle. Keep that in mind. This half angle is theta, and the mass of the body, this mass of the particle here is m, is moving in the circular motion inside a cone which is frictionless. This is the problem. A frictionless cone, a body moving inside it in a circular motion, frictionless, with mass m and acceleration and velocity of that very particle, velocity of particle is v. Okay, so we have to find the radius of circular path in which the particle is set in motion, circular path. So we have to find this r. R is unknown here, so we have to find the circular path radius. Okay, so how to find out that? Keep this diagram in mind. We have particle moving along a circular path. The conical half angle is theta, velocity is v, and the mass is m. So how to determine this sort of problem? So keep this here in mind that body surface is frictionless, so no contribution from frictional force. The only force which will be exerted onto this body m will be either contact force between the walls of the cone and the body, and the downward force, which will be the weight. So draw the free diagram. First of all, draw the free diagram. Draw the free diagram. Okay, how that is drawn? I will say this is the wall of the container, that is the conical shape, which I have shown you here. This is the wall of the cone. Onto it, the body M is here. It is moving in circular motion. It is set in circular motion like this. Circular path is like this. Okay, this is the circular path. The different kinds of forces which are acting over this, and keep it in mind, this is the half angle of the cone, which I have shown earlier. This is the theta. Okay, first and foremost, to draw the free diagram as follows. The downward force will be mg, because the mass of the body is m, so the downward force with the weight of the body will be mg. Another thing, the normal force will be perpendicular to this surface, because normal force is always normal, meaning the perpendicular to the surface, and that will be given like this. This will be the perpendicular n. So it will be perpendicular to the surface of the cone. Now, only these two forces are acting on the body. No frictional force, no external force. All external forces are absent. All external forces are absent, that is zero. Only these two forces are acting. So since the body is set in motion in the prior time, and now no force is acting on it, only the downward force due to the body itself, that is the gravitational force caused by the gravitational force, that is the weight of the body, and the normal force due to the contact between the body and the surface. So we have to divide it into the component form, because we have to see which component contributes to the motion along the circular path. And to set a body in circular path, we need a central force, that is the centripetal force. Centripetal force is we can say is required for a body to set it in motion, for a body to remain in circular path. Okay, so we have to find that very circular motion, that very centripetal force. Okay, and that very centripetal force will be toward the center of the circular path, not the center of this cone, but the center, even though that will be the center of the cone, as well at that plane. Okay, so that will be center of the circular path. So divide these very forces in the component form. We will get it as follows. This very thing, normal force, draw this very mg. It will be divided in, first and foremost, this is the theta, this is the slant height, this is the direct height of the cone, and this is the downward force mg. These two lines are parallel to each other, and this very is intersecting these two. And we know from the law of intersection of the two lines, if two lines are drawn parallel, and if two lines are parallel and intersected by another line, then this very angle and this very angle are equal. This very angle and this very angle, these two are equal, because these are interior angles between the parallel lines. Okay, similarly, this very angle and this very angle is equal. Fine. So here, this very angle and this very angle will be same from the law of intersection of the lines. So this will be theta. This is a mathematical formulation. You have already seen these very things in the earlier classes as well. So this very angle is theta, this very angle is theta. So here the component will be this very thing, and this will be the cosine component of mass times gravity. So this will be the mass times gravity cosine component, because it is along the component of the theta. Okay, similarly along the perpendicular, it will be mass times gravity into the sine component, because it is the perpendicular to this very base. Okay, this will be the cosine component. Similar, you have already seen it. If we have two perpendiculars and a vector in between like this is the vector v. and this is making an angle theta with this axis, say this x component is y. Okay, then along this very axis the vector will be, the projection of the vector will be v cosine of theta. Okay, and along y-axis it will be v sine of theta, the projection of this very thing. So this will be the v sine of theta, and this will be the v cosine of theta. Similarly here, mg sine of theta along this very axis, mg cosine of theta along this very axis. Similarly for n, we have draw the perpendicular upon this. So here the perpendicular on this is this line, and the perpendicular on this very thing is this line. So the angle between these two is also same as that of theta, because we know that, note it down, angle between two lines is equal to the angle between their respective perpendicular lines. So that means if we have two lines here, one is like this and another is like this, if this is the angle theta between these two lines, then the perpendiculars to these two lines, they will also meet at some angle, and that angle will be similar to that of the theta. That means if we draw this very if we draw a line perpendicular to this very line, say like this is perpendicular to this on here, and a perpendicular to this will be perpendicular to this. Okay, then the angle this very will be theta. Similarly this will be also theta. Fine. So this will be the angle similar to that of the theta, because these are perpendiculars to these original lines. Similarly here, mg sine of theta along this very axis, mg cosine of theta along this very axis. Similarly for n, we have draw the perpendicular upon this. So here the perpendicular on this is this line, and the perpendicular on this very thing is this line. So the angle between these two is also same as that of theta, because we know that, note it down, angle between two lines is equal to the angle between their respective perpendicular lines. So that means if we have two lines here, one is like this and another is like this, if this is the angle theta between these two lines, then the perpendiculars to these two lines, they will also meet at some angle, and that angle will be similar to that of the theta. That means if we draw this very if we draw a line perpendicular to this very line, say like this is perpendicular to this on here, and a perpendicular to this will be perpendicular to this. Okay, then the angle this very will be theta. Similarly this will be also theta. Fine. So this will be the angle similar to that of the theta, because these are perpendiculars to these original lines. Similarly here, this is the perpendicular to this very thing, and to this very thing this normal is perpendicular. So the angle between these two will be same as that of angle between these two. So you have seen the free diagram. Okay, so the free diagram of the given problem in the conical section, in the conical body moving in a circular path, the free diagram is like shown like this. So the n will be divided into two components as well, and along this very thing it will be n, along theta it will be n cosine component, that is cosine of theta, and perpendicular to it it will be n sine of theta. Now the free diagram is complete. See this, observe this very free diagram keenly. You will get the answer yourself. Keep that in mind. this n sine of theta is equal and opposite to that of the mg, the downward force. Okay, because it is the same force observed, it is the same force exerted on the surface of the cone by m, and the same force is exerted downwards, that is the weight of the body, same body m. Okay, this cosine component, it will not be cancelled out by anyone. This n normal force will be cancelled out by this very n, the perpendicular, that is this very mg sine of theta, because all these forces are exerted on the surface by the similar body m, which is the body m here. Okay, so all of these will be equal but component wise. So this very component cancel out this, and this very component cancelled out this. But we have to keep in mind the body is set in motion due because of some central force, that is the centripetal force, which I have told you earlier, and that very centripetal force is toward the center, and that very thing is the n cosine component, because this is the only force component which is not cancelled out by anything, anyone, any force. Okay, so the centripetal force is due to the contribution of this very component only, that is n cosine of theta. And we know the centripetal force with for a body with velocity moving with a velocity v, it is given as mass times mass of the body into velocity squared divided by r, where r is the radius of this very path. Okay, circular path. So this is the centripetal force. This force n cosine component as n cosine of theta, this component is not cancelled out by any other force. All other forces, this n of theta is cancelled out by this mg. So we know also this very thing, n sine of theta, will be equal to mg. Okay, so this very component, these are counterparting each other. So opposite, equal and opposite forces to each other. N sine of theta will be equal to that of the weight of the body, mg. Fine. Similarly, these two will be cancelling out each other, but we need only these two, a and b, equation a and b. So dividing, we can say divide equation b by equation a. We will get, upon dividing equation b by equation a, we get n sine of theta divided by n cosine of theta equal to mg divided by mv square by r. In the question is that find r, that is the radius of the circular path, okay, in which this body is moving. So we have to find this r, and that r is this very r, because this is the centripetal force, this very thing is the centripetal force, and the centripetal radius is r here, this very thing. So we have to find out this r. Fine. So here eliminating n, it will be eliminated. So sine of theta divided by cos of theta, it will be tan of theta equal to mg. In the denominator we have a by b form. Since, for example, we have a component a, we have a problem like this, a divided by x by y. If we can write it down as a multiplied by this, denominator is converted into the multiplication, and we have to write the reciprocal of this very thing. You might be aware about this. So we will write it down as mg multiplied by reciprocal of this, or mv squared. Fine. So in other words, the r will be equal to, this r will be equal to the tan of theta tan of theta mv square multiplied divided by mg. M and m goes, so the final result will be the radius. The radius of the path will be equal to tan of theta v squared divided by g, the gravity of the earth. So this will be the radius of the circular path. I hope you have got it quite well, since it has gone lengthy, but I am trying my level best to make you fully understand what kind of nature of the forces are here in this example or a particular example. So what I mean to say is that first and foremost, try to understand the problem and draw the free diagram, because drawing the free diagram is most compulsory and most easier way to tackle a problem. If you have drawn a diagram, pre-diagram perfectly, then you can solve the problem very easily. So that's why I have taken a lot of time on this problem in order to make you understand the free diagram of this very problem. So hope you have got this very problem as well. And furthermore, if you have any queries regarding this very problem or the earlier ones or any misconceptions. Coming to another problem, we have another problem on the similar concepts on the first law, second law, and third law of motion, and the circular motions as well. So we have consider an inextensible string which is not stretched, I mean to say that, okay, of length L. Length is L, keep that in mind. Length is L and the mass of the string is M. Length is L, mass is M. It is fastened on a circular roller like this in a loop shape, okay. This will be some pulley type shape is there. This will be some pulley. Fine. I know this is a rough diagram and a very much bad diagram. I'm not so expert in drawing the diagrams. Kindly try to focus on the concept only, okay? Don't look over the diagram. This is a rope or a string, fine, which is rolled over onto a pulley in a circular loop. It's forming a circular loop. Fine. And keep that in mind, the radius of the pulley is almost the same as that of the radius which will be formed on the string, because string will exhibit some circular shape. It will be having some radius, or it will be same radius as that of the pulley. Fine. We have to find what is the problem now, and the pulley, the angular velocity of the pulley, which ultimately will be that of the string, because string is attached to the pulley, is omega. Okay, so that means the angular velocity is omega. Fine. We have to find the tension upon the string. This is the string. We have to find the tension upon this string, tension T. Okay, this is the problem. An extensible string of length L and mass M, moving up on a roller coaster, on a roller, or we can say pulley with angular velocity omega. Okay, and we have to find the tension applied onto this very pulley, onto this very string. So we can take this problem as, we can solve it as, first and foremost, draw the free diagram. I have told you earlier, draw the diagram as neat as possible and try to focus on that. Say, for example, consider the elementary length of the string, string of mass delta m, that is small mass. Okay, like this. If we consider only this very thing, this very small mass, okay, of length, this very thing, fine, and the length will be given as that of, we know this is small arc of the bigger circle, and for a circle, the arc, this is the arc, and the arc length is given as equal to the radius times multiplied by the angle which it traverses, that is theta here. Say this is the theta. So we have to draw the diagram first. Take this elementary length of the string, say this much, and it says, say like this. This is the angle, small angle delta theta. Okay, so this is the this is the zoomed version of this very small portion. Okay, so this arc, this is the arc, this very arc, we have taken this very arc with mass delta m, and the angle, this very angle is delta theta. Fine, so that means the half of angle perpendicular to it, the half angle will be equal to delta theta by 2. Fine, so this is the elementary length. The tension will be over all the elementary particle, all the elementary masses of the rope. So onto here, the tension will be like this. On here, the tension will be like this, in the same direction as that of the tangential component. I can say the tangential component of the tension will be here at T, here it will be as T. But we have to keep in mind that draw here the parallel line to this very thing. If this is delta theta by 2, so that means this will be also delta theta by, sorry, not very, this very thing. This is the T. Okay, this is the tension. We have two components like this. This will be the component along the theta. This will be the theta, because this is the perpendicular to this. This will be the T cosine of component, cosine of theta, and along this will be the T cosine of theta, and theta here is delta theta by 2. It is delta theta by 2, the half angle. Okay, because this very is perpendicular to this. I had told you earlier that the angle between the lines is equal to the angle between the perpendiculars of the respective lines. Okay, so that means if this is the perpendicular to this and this is the perpendicular to this very line, that means angle between these two and angle between these two will be same. So this angle will be delta theta by 2, same as that of the this very thing. So this will be the cosine of component of the tension, and along downwards it will be T sine of theta, and that is delta theta by 2. Similarly here it will be T sine of theta by 2. Fine, so this will be the diagram of this very problem. So I will draw it again for the convenience. This is the string, this is the half angle, like delta theta by 2. This will be T, this will be T, and along this very component, this will be t cosine of delta theta by 2. This will be t cosine of delta theta by 2. And along this, it is the t sine component. This will be also t sine, because this is theta, delta theta by 2. This is the delta theta by 2. Delta theta by 2. So this will be t sine of delta theta by 2. Fine. Because this angle and this angle is same. This angle is same. Fine. As I shown you earlier, the angle between the perpendicular lines. So if we consider this as positive axis, so this will be positive, but this will be negative, and these two components are same and cancel out each other. So that means this and this cancel out each other, because it is in positive direction, it's negative direction with the same magnitude. So these two components cancel out each other. Now the remaining component is this sine component. This is having the same direction as that of this very thing. So sine components adds upon 2 times. And these two forces, these two tension components, these contribute. So sine component of the tension, sine component of tension T contributes to the centripetal force, because I have said you centripetal force. I have told you earlier that this very string is moving on a roller in circular path with angular momentum, with angular velocity as omega. So that means it will be set in circular motion with some centripetal force, due to some centripetal force, and that centripetal force is contributed by sine component of the tension. So we know this centripetal force is equal to mass times omega square r, where omega is the angular moment, angular velocity. So we have Fc equal to mass of this very component of the string. It is delta m, because this is the elementary particle of the elementary size of the original string. So delta m multiplied by omega squared r. R is the radius of the string, of the circular string, which is forms around the roller. So we have Fc is t sine of component 2 times, because these two contribute in the same direction. So we have Fc equal to 2t of sine of delta theta by 2 equal to delta m omega square r, because t sine of theta component, these contribute 2 times. So that's why this component also contributes to the same centripetal force. This component also contributes this, so 2 times t sine component. Okay, so but since the delta m length, we can write it like this: length of delta m is very small. So which in turn means that delta theta will be very small, that is very smaller than 1, which in turn means that delta theta by 2 will be very small. And in that case, if the angle is very much smaller, then we know that the sine of theta is equal to theta when theta is very small, that is very less than 1. So that means the sine of theta, delta theta by 2, since delta theta by 2 is very small, so that means sine of theta will be equal to theta itself. So we will write it down as 2t of sine of theta. Instead of this, we will write down by theta by 2, because this is the angle here. This is the angle, because sine of theta will be equal to theta itself. So sine of delta theta will be equal to delta theta by 2. Fine. Got it? Will be equal to delta m omega square, or 2 and 2 cancel out each other. So we will get T delta theta equal to delta m omega square r. But delta m is the mass of this very string. Fine, delta m is the mass of this very string. Delta m is the mass of elementary length of the string. And how to calculate the total length, how to calculate the mass. This delta m is equal to the total mass of the string, capital M, divided by total length. M is mass of string, I have told you earlier, mass of string. L is total length, small l is total length. So the elementary length will be equal, elementary mass will be equal to m divided by L, that is this is mass per unit length, mass per unit length. I am teaching you slowly because it is not important to that you should be able to crack the problem in 1 second, but it is more important to understand the problem first, because only after that you will be able to crack it down in seconds. So that's why I am teaching you very much slowly, so as to make you understand the vigor of the problem. So this is the mass per unit length. So the mass of the elementary length will be equal to the mass per unit length into the length of the arc. Fine, which I have taken earlier. Length of the arc. And length of the arc is given as I will write it down as arc length. That's ALC. AL will be equal to the radius of the, for example, this is the arc, this is the theta, this is the arc length AL, this is the radius R. Then in that very case, arc length is given for any circle is given as the radius of the circle multiplied by the theta. And here, in case of this, it is delta m will be equal to m divided by L multiplied by length of the arc is R, and this theta is delta theta by 2 because it is smaller. Delta theta, sorry, not delta theta by 2, only delta theta. I will see it first. Yeah, this is delta theta half, so full will be delta theta. Fine. So arc length will be equal to R delta theta. So that means delta m will be equal to m or delta theta by L. I will write it down, capital L, okay? So substitute this very thing in the earlier one here. T delta of theta equal to delta m omega. I will write it down first. So we have T delta theta by 2 equal to delta m omega square R. Okay, delta omega square by omega square R. This is the centripetal force, the cosine component contribution only. So this T delta theta by 2 will be equal to delta m. Delta m is this very thing, mass per unit length into R delta theta, omega square R. Are you getting it? I have substituted this very thing here. So this very thing cancels out each other. So any other thing, this will be, sorry. These two cancel. It is not divided by 2. It is only delta theta here. Fine. It is not 2 here. Sorry. So this will not be there. So this will be T will be equal to m divided by L. R, and R is R square, that is omega square R square. and this is the L is the length of the string, and we know this string is over the circular pulley and with radius r. So the length of the string will be equal to the circumference of the circular path. This is radius r because it is similar to that of the circumference. Fine. So string length is actually the what? The circumference of the circle with radius r, and that is equal to 2 pi r. Fine. So the length of the string L will be equal to the circumference of the roller, this pulley, that is 2 pi r. So that means L will be equal to 2 pi r. Substituting this, so which in turn means R will be equal to L divided by 2 pi. Fine, because we know only two things: M is known, L is known. This R is not known. So that means we have to substitute this very L instead of R. So substituting here, we will get T equal to M divided by L omega square R square. R square here is L divided by this, that is L square by 2 pi square. And this will be equal to M divided by L omega square. L and L goes, it's only one L remains, divided by 4 pi square. That is M omega square L divided by 4 pi. This will be the tension caused inside the string onto this very pulley. So this will be the tension, total tension on this very pulley in terms of length of the string and the mass of the string, not the radius. Fine. So if radius is given, then we would have substituted this very, the essential formula will be this very formula, but since R is not given, we are dealing in terms of M and L here. So tension is given as this very thing. Fine. Hope you have got it. Kindly revise it if you have felt a kind of lengthy this very problem in time. We have been doing this very problem since a long time, even though it is simpler, but the main focus I have tried upon this very problem is upon this very thing, the diagrams of the problem set, because it is essential to understand how the problem works actually. Rather doing the mathematics, it is very much simpler. Doing the mathematics is very, very much simpler. But on the first instant, you have to understand how these components come in existence, how these are canceling out each other, and how sign component only remains there, and what are the contributions of different kinds of stuff. Hope you have got it. If not, revise the lecture again. I hope that you will get it, at least not in the second attempt you will get it. Even then, if you have any queries, please feel free in the comment section to comment it down. Okay, comment it down in the comment section. I will come to those very problems very much soon to answer those very questions as well. Hope to see you in the end.